Welcome students to the MOOCs lecture series on non-parametric statistical inference. This is lecture number 1. In this lecture, I shall first explain to you what statistical inference is. Basically, there are two types of statistical inference, one is parametric, other is non-parametric. I assume that most of you know at least the basics of parametric inference. Therefore, in this lecture I shall not discuss much of parametric, mostly my focus will be on non-parametric statistical inference. However, I will often draw comparison between parametric and non-parametric, so that you will understand where these techniques stand in comparison with your background knowledge of parametric statistical inference. So, let us first understand what statistical inference is. This is the process of analyzing a sample data in order to deduce properties of an underlying distribution of probability. Say for example, here is a population, there are individuals, the population may be very large and our aim is to understand certain properties of the population. Most important ones are the mean and variance. We cannot study the entire population if it is very large. Therefore, what we do? We sample some data from the larger population for which we want to infer. Therefore, what is being done? Suppose there is a huge set of data, we take a small sample, typically randomly chosen, and based on that our aim is to infer about this population, or sometimes we shall see that we compare two populations. Therefore, the basic tasks of statistical inference can be said. One is that estimation of distribution parameter, it can be comparing two population parameters, namely mean and variance. Say for example, here is a group of students and here is another group of students. We want to compare whether they have the same mean or they have the same variance, or if they are not same, what is the relationship between them. We try to get a feeling about that. And other thing is testing of hypothesis, which means that whether a sample gives enough evidence in support of some assumed value theta naught for some distribution parameter theta. Now, many of you may not know what I am meaning by distribution parameter. All of us, I hope, familiar with certain distributions, for example, normal, binomial, Poisson, etc. Whenever we talk about certain distribution, we associate with them certain parameters. For example, normal has two parameters, mu and sigma square. Binomial has two parameters, the number of trials and the probability of success. Now, these are important parameters for a distribution, because if you look at them carefully, you will see that the mean and variance come from the distribution parameters. For example, for normal the mean is mu, variance is sigma square, and they are involved in the PDF of normal distribution as parameters. For binomial, the mean is NP and variance is equal to NP into 1 minus P. Again you see that we can derive them from the parameters given corresponding to a binomial distribution. Hence, if we estimate the parameters of a distribution, then we can get a feel of the overall population. Now, robust statistical methods work under certain assumptions. By robust we mean typically the statistical methods that we use, namely say many of you know about Z test, T test, chi-square test, F test, etc. These are some robust statistical methods, but there are certain assumptions for them. In particular, most parametric methods assume that the data is quantitative. If the data is not quantitative, the statistical methods that we know will not work. Population has a normal distribution. It is an underlying assumption that the population with respect to certain properties will have a normal distribution, that is, it is central around the mean and it is more or less symmetrically spread around the mean, and the sample size is sufficiently large. That means, in order to infer for the population, we need quite a large sample size. But in practice, it always does not happen. For example, data may be ordinal or categorical. For example, when we talk about marks of the students, we may give them A minus, B minus, etc. in our IIT system. Therefore, in some sense all students getting a grade A are somewhat equivalent, but they do not have the same marks. Therefore, the data is no more numeric and therefore, we cannot process it using the standard statistical techniques. Data may be ordinal, that means we are ranking them as first, second, third, but we do not know the distance between the second and third and the distance between the first and second, etc. And that means that here I am saying that variables have natural ordered categories and distances between the categories is not known. I hope you understand by that. Suppose first boy is 80, second one got 75 and third one got 65. So, I will give them the rank 1, 2, 3, but if the first one is 80, second one is 78 and third one is 75, again they get the same rank 1, 2, 3. Therefore, when I have the data in this ordinal form, I lose a lot of information. Also, another problem is that the population size may be too small to be treated as normal. Therefore, the question comes, if the normality assumption is not there, then what we should do? There is one common technique of transformation of data. In transformation, what we do? If we take a function of the data, then we may get the normality assumption. Some standard transformations are log, square root, etc. Else what we can do? Else it is often advised to try with other known but non-normal distribution, say exponential distribution. That is another important thing that can be done. Or the third option is that we go to non-parametric mode. That means, now we are switching over to a non-parametric analysis of the data, and This is the focus of this series of lectures that I am going to present to you in this lecture series. Therefore, the basic question comes, what is non-parametric statistical analysis? A statistical method is called non-parametric if it makes no assumption on the population distribution or the sample size. Therefore, we are not having any restriction on sample size. You will see later that there are statistical tests on non-parametric way where sample size may be 2, 3, but still we can work with that small size data, and generally there is no assumption on the population distribution, but this is not quite correct. Sometimes we may have a very general assumption, as I am explaining later, but this is in contrast with distribution free. So, these two terms, distribution free and non-parametric, are not quite synonymous. They have a subtle difference. As I said here earlier, that non-parametric methods, they have very little or no assumptions required, but sometimes we shall assume that it is from a population with a continuous distribution. So, that is the only assumption. We are not talking about anything else. What does it mean? That the sampling that we are taking, that is coming from a continuous set of data, but the samples that we have taken, as you can understand, they may be discrete. Distribution free properties do not make any assumption about the sampled population. So, absolutely no assumption is there. So, there is a subtle difference. However, distribution free procedures were devised primarily for non-parametric problems. Therefore, often these two terms are used synonymously, but for this class we shall stick to non-parametric methods, and we are not going to call them distribution free methods, which you may often find in some literature. So, question comes, where do we use non-parametric methods? Very valid question. So, the following are some situations where the use of a non-parametric procedure is appropriate. The hypothesis to be tested involves no population parameter. As we have discussed some time back, that when we are talking about mean of a distribution, this actually can be found from the parameter of the underlying distribution or underlying PDF or PMF, like say normal distribution function or binomial distribution, Poisson distribution, etc. So, that is first thing. Second thing is that the data have been measured on a weaker scale, so that assumptions necessary for the valid use of parametric procedure are not met. For example, the data may consist of count data and rank data. Data may be qualitative, ordinal or nominal. I have in some sense explained this thing, so I am not going into details. We will come across them in course of time, but let me give you some example. In a class of 100, the CGPA distribution is not typically normal. If we look at the distribution of marks in a class of say 100, we will find that it is not normal. There will be a set of boys who are very good. Thus, at the right end of the data there will be high frequency. Similarly, somewhere near the pass and fail boundary there will be high frequency. In between it is not necessary to be symmetric. We have often seen distribution like this with respect to different grades like A minus, B, etc. The distribution of SGPA given CGPA is not homoscedastic. That means, even if we assume that the CGPA is given, then it is not mandatory that the semester grade point average will have equal variance along the or for the same CGPA. Say for example, when the CGPA is something like say 9 out of 10, you will find very low variance among the SGPA. But if the CGPA is something like say 7.5, we will find a wide range of variation in the SGPAs or the semester grade point average. So, homoscedasticity means that the variance will be same with respect to different points for SGPA, but that is not a very valid assumption with respect to the CGPA distribution. And if we consider a small class of 20 students, then such assumptions do not hold. Therefore, the question comes, what are the advantages of non-parametric statistics? It makes fewer assumptions in comparison with the robust statistical procedures. It need not involve population parameters. We are not bothered about the distribution parameters. As I said that we are not even assuming any distribution for the data which has come from the population. Small chance of being improperly used, because non-parametric methods have been developed for very specific purpose. So, it is very unlikely that you are going to use it in a wrong way. Applicable to data measured on weaker scale, as I have been telling that marks is a much stronger scale in comparison with grades, because it merges several marks into the same grade. Therefore, that is a weaker scale. It is easy to understand and involve less intricate mathematical statistical knowledge. We will be doing lot of mathematics in establishing or improving certain non-parametric results, but you will see that the mathematics is pretty simple, although laborious. Let me warn you at the very beginning that this is going to be little bit laborious, but simple. Computations are quick and can be easily performed, because less mathematical details and designed for small numbers of data, including counts, classifications and ratings. So, since these are working on a small set of data, overall computational requirement is less, and since most non-parametric procedures depend on a minimum set of assumptions, they have wider applicability. So, they can work on various types of data in comparison with normal parametric procedures, which work only under certain restricted cases. However, there are certain disadvantages also. We may waste some information, often actual values are not considered. For example, given the marks, we have converted them into ranks. That way we lose a lot of information. Therefore, that is one drawback. Manual computation is difficult for large samples, because as I said, the computation is laborious. If the sample size is large, then it takes quite some time to finish the computation. Tables are not widely available, say normal table, chi-square table, T, F, all these distribution tables, all those who are familiar with parametric inference know very well, but similar tables are there with respect to many non-parametric techniques, but those tables are less freely available. As we go through the series of lectures, I will refer to many different tables. I will give you links, and I shall also give examples of how those tables start to be read when you want to use them for your inferencing purpose, and definitely these are less efficient. If you can do something with a t-test or z test, that is going to be much more efficient to achieve the same efficiency level with respect to non-parametric cases. You may need a prohibitively large sample size. So, let us look at the most common problem, non-parametric estimation of location and dispersion. So, what do we mean by location? By location, essentially we mean the central tendency. When it is numeric case, we talk about mean. But mean, as I said, has come as a distribution parameter and we are not assuming any distribution. So, when we are talking about non-parametric, for us this is going to be median. I hope all of you know what is median. That means, it is the value such that 50% observations will be on left side of it, that is lesser than that, and 50% of the observations will be greater than this. Not only median, we can also talk about quantiles, that is, many of you know percentile, quartile, etc. So, we can even try to estimate this type of quantiles also. There is no problem that we can do using non-parametric methods. And dispersion, by dispersion basically we mean the spread of the data. With respect to parametric case, we use variance or range. We shall see how we use the data given for measuring the spread. So, this is the basic background. Let us go into some estimation first. For all p 0 less than p less than 1, let zeta p denote the pth quantile, that is f x zeta p is equal to p. So, suppose this is a distribution, this is the data, and suppose this is the f x, which you know is the cumulative distribution function. So, this point is called as zeta p if the proportion of observations less than this is p. Therefore, if p is equal to say 0.22, basically what we try to identify the point such that the proportion of observations below that is going to be 22%, and that is true for all p between 0 to 1. A point estimation of zeta p is often given by the corresponding sample quantile. That means, if this is the sample that is given, we will try to see which values are there from which I can get the zeta p. So, in order to do that, what we shall have to use is the rth order statistic. I hope all of you know what is an order statistic, but basically this is that suppose we have a sample, then we order them in terms of magnitude. The smallest one is x 1 and the largest one is x n. It is the nth order statistic, it is the first order statistic, and the rth one in number, that will be called the rth ordered statistic. Therefore, this is a random variable, we put it with capital X. When we are looking at small x, this is basically the observation. Now, n is the sample size. If n plus 1 times p is an integer, that is p is equal to r upon n plus 1, p is equal to r upon n plus 1, then xr is the point estimate of r by n plus 1th quantile. However, n plus 1 p is not an integer, that is the most likely situation. Then p will be lying between two observations, the rth one and r plus 1th one. Say p lies between, this is the rth observation in terms of order and this is r plus 1th observation, then p is suppose lying somewhere here. Then we have to do an linear interpolation of these two values, these two observed values, to get the estimate of zeta p. So, if we use the linear interpolation, then zeta p is going to be n plus 1 p minus r plus 1 upon r minus r plus 1 into xr. xr is the rth order statistic, that is the rth, all the observations, the one that is rth smallest, that is going to be called xr, and this is therefore going to be r plus 1th smallest, and I am going to interpolate between them, and from there we are going to get a value for zeta p, that is p is lying somewhere between r upon n plus 1 to r plus 1 by n plus 1. So, let me give you an example. Suppose I have observed this set of data. There are 11 information 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What does it mean? That suppose this is a set of possible values, we have considered 11 observations from this line. We need to find out what is the 0.25 quantile, that is p is equal to 0.25, and what is the pth quantile when p is equal to 0.35, when n is equal to 11, and these are the observations. So, how will we proceed? We first compute the order statistic. That means, we have sorted the values from the smallest to the largest. The smallest observation has been 5.6, second smallest is 8.8, like that. 8th one is 36, 9th one is 38.7, 10th one is 43.5. So, this is the order statistics of the observed data. Do not forget that that is the order in which we have sampled. Sample might have come in this order as given there, but when I sort the observations, I get this sequence. So, n is equal to 11, therefore, n plus 1 is equal to 12, and we are looking at the zeta p when p is equal to 0.25. Therefore, n plus 1 times p is equal to 3. Therefore, zeta 0.25 we can replace it with x 3, that third order statistic, which is 11.4. What does it mean? This inference says that the population is such that 25% of the observations are going to be less than equal to 11.4. Very, very simplistic thing, but that is how practically it works. Now, let us consider p is equal to 0.35. Therefore, n plus 1 p is equal to 12 divided to 0.35, which is coming out to be say 4.2, because n plus 1 is equal to 12, it is 4.2. Therefore, we see that n plus 1 times p lies between 4 and 5. which implies that 4 by n plus 1 is less than 0.35 less than 5 upon n plus 1. Therefore, we have got r is equal to 4, r plus 1 is equal to 5. Therefore, P is lying between these two. Therefore, what we can understand that the 0.35th quantile is the linear interpolation of the fourth order of statistic and the fifth order statistic. Therefore, using the interpolation we get that the value is coming out to be 20.82. What does it mean? It means that the 35% of the observations are going to be less than equal to 20.82. Therefore, without knowing anything about the scale, whether it is from 0 to 100 or say from 5 to 75, we get a feel of what is going to be the 35th quantile of that one. Okay? So, that is the simplicity for non-parametric estimations, but you should understand that it is the simplest type of inference that we are going to do in a non-parametric way. Now, question comes about interval estimation. Say suppose this is the observed data, this is my zeta p. This is done on the basis of the sample that we have. But perhaps most of you will say that based on one sample, how can we say that this is the actual pth quantile, which is very obvious. Therefore, what we try to do, we try to build a confidence interval around the point that we have calculated, such that we can be confident enough that zeta p will lie within this interval. Now, this size of the interval will depend upon the level of confidence, which we call alpha. Therefore, if alpha is equal to 0.05, that is 5%, which is between 0 to 1. Therefore, effectively we are looking at 100 into 1 minus alpha, which is equal to 95% confidence interval. I hope most of you have the idea about this, but still I am explaining it. What does it mean? It means that although we have done it on the basis of one sample, 95% confident that the zeta p, the pth quantile with b will be within this interval, and the chance is only 5% that actual zeta p will lie outside this interval. So, this is what is called interval estimation. So, when we are going for non-parametric, we are looking for two values r and s such that the rth order statistic less than the zeta p, which is less than the sth order statistic, this probability is going to be 1 minus alpha. That is, if alpha is equal to 0.05, we are looking for probability that x r less than zeta p less than x s is equal to 0.95. So, our aim is to identify this r and s. That is, we can say that suppose x r is 5 and s is say 9. So, basically we are saying that zeta p will be between that fifth order statistic and the ninth order statistic with probability 95% or 0.95. Now, how to obtain this? Note that probability xr less than zeta p less than xs is equal to, what is the probability that xr less than equal to zeta p minus probability xs less than equal to zeta p, right? Why it is? So, consider the same r is equal to 5 and s is equal to 9. Therefore, the fifth order statistic is less than equal to x when first 5 observations are less than equal to x, but it is also true for first 6 observations are less than equal to x. It is also true if 7 observations are less than equal to x. Therefore, probability x 5 less than equal to x, where 5 is the fifth order statistic, is greater than the probability that the ninth order statistic is less than equal to x, because whenever this happens automatically this is going to be less than equal to x, but reverse is not true. There can be a situation when fifth order statistic is less than equal to x, but the ninth order statistic is more than x. Therefore, probability that zeta p is between xr and xs, what we will do? We shall subtract the probability xs is less than equal to zeta p from probability xr is less than zeta p. This is what I have written here, that for any p xr less than zeta p, if and only if at least r of the n sample values are less than equal to zeta p. Therefore, since x 1, x 2, x n are order statistics, if x I is less than zeta p, then x j less than zeta p for all j less than equal to I. That means, suppose this is my zeta p and I am saying that the fifth order statistic is less than equal to zeta p, that means that x 4, x 3, x 2, x 1 they are all less than zeta p. Therefore, probability x r less than zeta p is equal to exactly I of the n observations are less than zeta p, where I is equal to from r to n. As I have explained earlier, that x 5 the fifth order statistic is less than zeta p if below zeta p there are 5 observations, 6 observations, 7 observations, in fact all the n observations are less than zeta p. In all these cases x 5 is going to be less than zeta p. Therefore, this is clear. Therefore, probability exactly I of the n observations are less than zeta p can be found as the probability of I success defined as any observation being less than zeta p in n independent Bernoulli trials with probability of success is x I less than zeta p is equal to p. I hope you understood it, but let me explain again. So, suppose this is my zeta p, that means probability an observation is less than this value is equal to p, and probability an observation is greater than this value is 1 minus p. Now, therefore, when I am choosing a sample, it has a probability p to remain on the left side of zeta p and probability 1 minus p to be on the right side of the zeta p. Therefore, it is like tossing a coin. With probability of head is equal to p, right? Because if we take a random sample, there is a small p probability that it is on this side, which we are calling it a success, and if it is on this side, it is going to be a failure. and you know that in Bernoulli by hate we mean the success. Therefore, we are trying to compare this situation with a Bernoulli tossing situation. Thus, required probability is a binomial probability that out of n tosses, r of them are less than equal to p. Therefore, probability exactly I of the n observations are less than zeta p, that probability is coming out to be NCI p to the power I 1 minus p whole to the power n minus I. This is coming from binomial distribution. Therefore, probability x r less than zeta p, I am summing over I for r to n NCI p to the power I 1 minus p whole to the power n minus I. Therefore, probability x r less than zeta p less than x s, we can see is that is equal to probability x r less than zeta p minus probability x s less than zeta p, which is same as I am summing for I is equal to r to s minus 1 NCI p to the power I 1 minus p whole to the power n minus I. Now, when we are going to use this for interval estimation, therefore, we want that if I want a 95% confidence level, therefore, we will look at that I need an S and R such that this probability summation over I is equal to r to s minus 1 of NCI p to the power I 1 minus p whole to the power n minus I is greater than equal to 1 minus 0.05, that is 0.95. Therefore, for 95% confidence interval, we are looking for R less than S, this is less than equal to 1, this is greater than equal 1, such that sigma over I is equal to R to S minus 1 NCI p to the power I 1 minus p whole to the power n minus I is greater than equal to 0.95 for 95% confidence interval if alpha is equal to 0.05. Similarly, for 90% confidence interval, value of alpha is going to be 0.1. Therefore, what we do for determining the confidence interval? There are different ways of choosing. Narrowest interval approach, choosing R and S such that S minus R is the minimum for a fixed alpha and involves trial and error solution to make this summation to be greater than equal to 1 minus alpha. So, what does it mean? Suppose the values are along this line x 1, x 2, again I tell you these are ordered statistic, this is not the actual first, second, third sample. Suppose this is how the values are ordered. I am looking at the 95% confidence level. Now, it can be that between these there are 95% observation. Similarly, it can be that between this and this there are 95% observation, or it can be that between this and this there are 95% observation. Therefore, question comes which R and S we should choose. The narrowest interval approach tells us that we will take that to be the 95% confidence interval which is of smallest length. So, in this case most probably this is going to be the 95% confidence level. Another way of looking at this is the following. This is called equal-tails approach. So, if we have the data like this, then we will partition it in such a way that on both the sides there are same number of observations. So, this is the 95% confidence interval we are going to consider. So, these are the two basic approaches for considering the confidence interval. So, this we obtain typically using cumulative binomial distribution table. Given n and p, we will try to see how to get the confidence interval. So, let me solve one example. Suppose you have sample of size 9, what is the confidence that the median is between x 3 and x 8, the third order statistic and the 8th order statistic. That means, we have 9 samples and we are looking at that the median will lie in this interval. What is the confidence? That is what we are trying to figure out. So, we go as follows. Probability that the median will lie between x 3 and x 8 is equal to summation over I is equal to 3 to 8 minus 1. Therefore, r is equal to 3 and s is equal to 8, and as we have summed earlier, for 3 to 8 minus 1, 9 C I p to the power I 1 minus p whole to the power n minus I. Here n is equal to 9. Therefore, this is equal to 1 minus probability I is equal to 0, I is equal to 1, I is equal to 2 and I is equal to 8 and I is equal to 9. So, I am just taking out all those things which are not included, and that comes out to be, after this arithmetic, 0.89. Therefore, the confidence that even if you choose any random sample of size 9, then the median of the population will lie between the third and 8th order statistic is confidence is 0.89, that is nearly 90% confidence interval. So, this is the basics of point and interval estimation, and this is the very simple of the problems that we will be dealing with for non-parametric tests. So, under non-parametric setup, the type of problems that we take up are of different types. So, let me discuss the problems that we are going to take up in this series of lectures. So, first one is of testing of hypothesis about the central tendency of the distribution. So, the problem is specified as, suppose we have taken a sample x 1, x 2, x n from the population. Question is how to test the central location of the population is actually mu naught. So, mu naught is a given value and we want to test whether this sample gives us enough evidence that the sample has come from a population with central location mu naught. In parametric setup, the test is done using z test or the normal test, where the test statistic is x bar minus mu naught upon sigma by square root of n, where x bar is the sample mean and sigma is the known standard deviation and n is the sample size. Alternatively, one can use one sample t test with n minus 1 degrees of freedom, when sigma is unknown. The corresponding statistic is therefore going to be t with n minus 1 degrees of freedom, which we write as a subscript, and the statistic is defined by x bar minus mu naught upon sample standard deviation, which is s divided by square root of n minus 1. I am sure most of you are familiar with these tests, but I am providing here for some recapitulation. For non-parametric test, sample mean is replaced with sample median, and the corresponding important tests are sign test and one sample Wilcoxon signed rank test. In this series of lectures, we shall study these two tests in detail. Another important problem is test for location for a paired sample. For a parametric case, paired t test is done here, and it is based on the difference between two values of a pair of observations x I comma y I for I is equal to 1 to n, where n is the sample size. We shall discuss paired test in detail later, but basically on the same sample we take two observations x I and y I, and the statistic is computed on the basis of their difference, which typically we denote by d I. Therefore, corresponding t statistic again with n minus 1 degrees of freedom comes out to be as given below: sigma d I divided by square root of n into sigma d I square minus sigma d I whole square divided by n minus 1. So, for non-parametric case, the major tests are paired sign test and paired Wilcoxon signed rank test. Another type of problem is equality for central location of two samples. So far, the two tests that we said, it is one sample, but now the motivation is to compare the central location of the two populations where from x and y have come. So, in order to do that, what we do? We take samples x 1, x 2, x n and y 1, y 2, y m, say from x and y population. If we want to do z test, then corresponding statistic is x 1 bar minus x 2 bar divided by sigma 1 square by n plus sigma 2 square by m, where sigma 1 is standard deviation for x and sigma 2 is standard deviation for y, and n and m are corresponding sample size. X 1 bar is the sample mean for x population and x 2 bar is the sample mean of y population. If we know that sigma 1 and sigma 2 are same, then the statistic becomes slightly simplified. As you can see, we just take out sigma from the square root, and therefore, this is the statistic when we are knowing that sigma is same for both the populations. However, when the variances are unknown, then it is replaced by a common variance, and that is typically estimated by n minus 1 s x square plus m minus 1 s y square divided by m plus n minus 2, where s x square is the sample variance for x, s y square is the sample variance for y. So, this is what we do for parametric case. For non-parametric case, two major tests that we are going to study are Wilcoxon rank sum test and Mann-Whitney U test. Scale problem, this is another type of problem that we will be handling. Here we want to test the dispersion of two samples. For parametric case, suppose x1, x2, xm is a sample from x population, y1, y2, yn is a sample from the y population, and we are trying to test that whether they have the same variance. The corresponding statistic is F statistic, which is computed by the ratio of the two sample variance. We shall talk about it later when we come to the scale problem, but for non-parametric scale problem there are many different tests. In particular, we shall study mood test, Freund-Ansari-Birdley test, David-Burton test and Shukhatme test. Goodness of fit is another type of problem that we shall handle in the non-parametric statistical inference. Here the two major tests are frequency chi-square test. It considers the difference between the actual frequency and the expected frequency for each class, and the statistic computed is following chi-square distribution, hence it is called chi-square test. And another important test is Kolmogorov-Smirnov one sample test, which is based on the order statistic of the sample data. In a similar way, slightly more extended version of Kolmogorov-Smirnov one sample test is called the two sample Kolmogorov-Smirnov test, and also there is something called median test, which are commonly used to compare the distribution of two different populations. We shall study them as an extension from Kolmogorov-Smirnov one sample test. Apart from the above, there are also tests for testing randomness of a data. That means, the sample that we have taken, whether it is actually collected randomly or not, that itself is necessary to judge before actually putting it for some inference mechanism. Therefore, we need to first check if the data is actually random, and there are several run tests that allows us to see the randomness of a given data. Furthermore, we shall study statistical measures such as Spearman's rank correlation and Kendall's tau. These two are important for measuring association between two data samples. In case of parametric inference, we use covariance or correlation coefficient for measuring the association between data. For non-parametric case, we shall look at these two tests in detail. Finally, we shall study Kruskal-Wallis test, which is to compare the distribution of more than two populations. So, we have mentioned about one sample, then two sample. What happens if we want to test the equality of distribution of more than two samples, say k samples, where k is equal to 3, 4, 5, etc. The corresponding test is called Kruskal-Wallis test, and we shall study it towards the end of this lecture series. So, these are the major non-parametric tests that we shall study in course of time during the lecture series. So, over the next 9 lectures, we shall learn these major non-parametric tests with great details, with solved examples, and also I shall show you how to check the test from the tables, or how to see the tables to understand whether to accept or to reject a particular hypothesis. Okay, friends, I stop here today. From the next class, I shall start with different non-parametric tests. Thank you.